And now I'd like to introduce our presenter. Jeremy Klein is a product manager and is responsible for EMC products and systems for Rohde & Schwarz North America. Over the last 9 years, Jeremy has specialized in both field and lab applications for multiple industries and has authored several white papers and patents. So without further ado, let's turn our attention to modern EMI receiver measurements, concepts, and 5G MmWave Spurious testing with Jeremy Klein.
Okay, great. I'd also like to extend a very warm welcome from my side. I certainly appreciate everyone being here for today's presentation. I'm excited to have the opportunity to speak to all of you about the modern concepts of EMI test receivers and how they can help with 5G testing. I think there's a lot of focus today on the 5G wave and how everyone could get a cut of that business. I'm from the EMC side of Rohde & Schwarz, and I don't think that EMC typically is the first thing that comes to mind when someone mentions 5G testing, but there are certainly some very important tests that must be made. In particular, radiated spurious emissions will be the main focus of today's discussion. So for today's presentation, my goal, if you will, is to answer this question of the day about how can EMI test receivers help with 5G testing? And to answer that question, I'm going to split today's presentation into 3 major parts. We're going to step back and look at some 5G basics. I think that'll kind of set the stage for today's discussion. Then we'll look at the testing challenges that 5G brings with it. And last but not least, we'll kind of map that over to answer today's question. We'll focus on test receivers and how they can actually help with 5G testing. So without further ado, I'd like to jump into 5G basics. I think one of the most fair questions you can ask when it comes to 5G is, where do we stand? Now, the answer is probably going to change depending on who you ask. If I answer that question, I'm going to say we're still at the standard stage, and you'll see why as we go throughout the presentation today. But regardless, if you're talking about 2G, 3G, 4G, or now 5G, every G wave, if you will, follows the same exact pattern, which is shown on the graphic on this slide. Typically, you'll start with a bunch of research, you'll have some prototypes, of course you eventually get to field trials where you try things out. This is really where you're actually experimenting with the physics of how things are going to work. Now with 5G, of course, you have the FR1 frequency band and you have FR2. A lot of the most interesting work is in FR2, that's your millimeter wave frequencies. You have much higher degrees of attenuation when you're up that high in the frequency band. And you also have a lot of multi-wave effects, so on and so forth, which is classic RF challenges. Once you get past that stage, then you get into the standardization stage. This is where bodies like 3GPP and FCC and ETSI actually outline the requirements and specifications of how the actual protocol itself is going to work. This is a fairly extensive process. This has actually been going on for several years now for 5G. And like I said before, I think we're still in this stage. Once all of that matures, eventually you're going to have commercial products come out, and of course, a full-on rollout where the network operators turn on 5G signals and everyone starts making phone calls and downloading YouTube videos and so on and so forth. But the main takeaway here, like I said, is that we are still in that standardization stage, and I think you'll see why as we go through the presentation. Now, one thing's for sure, there has been a lot of work with standardization for 5G, and this slide focuses on the 3GPP work plan and priorities that we've seen in calendar year 2019. Now, I'm not going to go through every single detail. I'm going to leave this slide up for you to study a little bit. But what you'll see is this is very classic for any G wave. There's a lot of work around network efficiency, interference mitigation, and power consumption for the UE. That's another name for your mobile device. And with 5G, there's a lot of focus on automotive concepts like V2X. Of course, you have the Internet of Things, you have public safety networks, and all of these different concerns. But one thing that should stand out to you, and I know it stands out to me, is there's no mention here about EMC. So the real question remains, is there something going on with EMC? Yes, we just have to dig a little bit deeper. So let's do just that. This slide and the next slide are going to look at the 3GPP new radio specifications. And what you'll see is that these specifications are divided into four major parts. You're going to have RAN 1, RAN 2, and on the next slide, we'll take a look at RAN 3 and 4. But as a quick overview, if you look at these different specification areas, RAN 1 really focuses on your physical layer requirements, and RAN 2 focuses mostly on protocol. So we don't see any EMC here. If I look at RAN 3 and 4, RAN 3 really focuses on your layer 1 information and signaling, and RAN 4 is finally where it gets interesting from my perspective, because if you look down at the bottom, you get some EMC requirements for the base station, your mobile terminals, and ancillary equipment. That's some fancy wording, but again, if we dig even deeper into these, you're going to find RSE requirements. Before we do that, I want to make sure everyone understands exactly what RSE is. So RSE stands for radiated spurious emissions, and I want to take each one of those words and kind of break it down so we truly understand what we're dealing with. R stands for radiated, and if you're at all familiar with EMC measurements, you know that there's typically two ways to perform EMC measurements. You have conducted, which suggests that you are physically connected with something like a cable, or radiated, which suggests that the signals are transmitted over the air and you're using an antenna to receive and analyze those signals. So in this case for RSE, we're doing everything over the air. So the E of RSE stands for emissions. And this refers to all the signals transmitted, including harmonics and other mixing products. If you now look at the figure at the top right-hand side corner of this slide, this is really what I'm referring to. Typically at F0, you have your fundamental frequency. This is what most people care about because it's the most signal energy and all of your data that's carried. You might have modulation and so on. Everyone typically wants to look at that. But basic RF principles say that every fundamental frequency or signal also has harmonics. You can have a second, third, fourth harmonic, and so on. And even with those harmonics, if you have dissimilar metals or something like this, those signals can bounce around and have something called an intermodulation effect. You can get some spurious emissions. And that's really the SE of RSE. Spurious emissions really refer to those spurs that are kind of interspersed among the harmonics. You can see just how many individual signals exist because of just one fundamental frequency that you actually care about. So the standardization bodies like FCC, ETSI, so on and so forth, they have requirements that actually look at these spurious emissions to make sure that they are not too high in signal level such that they would interfere with another device, for example. Now, the formal definition on the slide here talks about spurious emissions refer to everything except the fundamental frequency, and they lay outside the out-of-band emissions. And what I really mean by out-of-band is shown in the graphic at the bottom, figure 2 there. In the center, you have your F0, that's your fundamental frequency you care about. And then you look at some bandwidth just outside that area. That's really where the out-of-band device emissions are. But even outside of that, at the very outer edges, this is where you're going to find your spurious emissions. So radiated spurious emissions, or RSE, the takeaway here is that they typically come from what's known as an intentional radiator. That's just the device that you're testing. It's putting out a fundamental frequency and all these other emissions and spurious emission products. And those are really your unintended RF emissions that you need to measure and make sure they stay under a certain level. So shown here is an example of an RSE test. In figure 3, you can see that there's a red limit line labeled regulatory limits. I just mentioned that spurious emissions cannot be too high in signal level. So in this case, you're looking at the device emissions trace in blue. In this case, it was measured from 30 megahertz to 1 gigahertz, and you can see all of the different spurious emission products stay beneath that limit line. This would be an example of a test that actually passed. Now, it's important to note that RSE is typically performed within a chamber. And the reason you want to do that, again, since this is a radiated measurement that suggests you're doing things over the air, you don't want to get signals accidentally, for example, from the RF environment outside of what you're trying to test, which is your device. Examples would be radio or Wi-Fi or Bluetooth, something like this. If you go inside of a chamber, you can block out all other signals from the environment you're testing in so that you can just focus on your intentional radiator, or again, the device you're trying to test. You measure all those harmonics and make sure that they don't go beyond a defined limit line. Now, it's important to realize RSE has actually been around for a long time. This is not something new to 5G. RSE has actually been used to be tested for GSM, for 2.4 gigahertz ISM, which is the industrial scientific medical band. It's unlicensed spectrum in that case. 40 gigahertz equipment. I've actually provided the standards here if you want to go look at the details. One example is parts 22 and 24 from FCC. There's a table here on the right-hand side of the slide that provide all the details. One thing I will point out right now, if you want to commit it to memory, is that the power limit is minus 13 dBm in that particular standard. You'll find out later in this presentation that minus 13 dBm is used again for 5G. But if you want to look into those details, feel more than free. I'm not going to go into more detail right now. One thing I do want to point out is if you go look at these standards, you'll find out that EMI test receivers are not required, which is pretty interesting since I'm giving a presentation about how EMI test receivers help with 5G RSE testing. So the point here is you can use spectrum analyzers, and that's completely fine. Most EMC customers like to do other types of testing aside from RSE. But if you do have a case where you're just performing RSE, you can get away with not using a test receiver. And some people might make the argument it makes sense because the typical EMC bandwidths, like 200 hertz, 9 kilohertz, and so on, are not even called for in the RSE specification documents. So you're not even using typical bandwidths a receiver might offer. You have to use some other bandwidths that are not typical. The other thing is you have to use some filters. In EMC, we typically use 6 dB filters. RSE calls for 3 dB. So that's another difference. And last but not least, typically for RSE, you're going to use the peak detector. EMC measurements usually use something called a quasi-peak detector, which is a time-weighted average type approach, and you don't need it. So again, you could use a spectrum analyzer, but as we'll go on through this presentation, I think you'll see, even aside from these three things here, you still might want to use a test receiver. Okay, I think that gives us a good foundation for 5G basics. Let's move into some of the testing challenges that 5G brings. As you might recall from early in the presentation, I mentioned that 5G has two basic frequency ranges. They're most commonly referred to as frequency range 1 and frequency range 2, or FR1, FR2 for short. FR1 is your sub-6 gigahertz band. It goes from 450 megahertz to 6 gigahertz. And FR2 is your millimeter wave frequency band. This is where all the interesting work is happening. And it goes from roughly 24 to 53 gigahertz. I also provided the 3GPP new radio specification review we talked about earlier. Just as a reminder, this first part right up top talks about the RF test specifications for user equipment and base stations. This is where the RSE requirements are. But now I'm kind of mapping this over to some basics and really spelling out the challenge. It's really as simple as just the frequency. If you're familiar with test equipment out on the market that's available, especially as it pertains to test receivers, you know that receivers these days only go up to 40 to 44 gigahertz. You won't find a base unit receiver that goes beyond that point. So how would we measure 53 gigahertz roughly for FR2 with a 44 gigahertz receiver? This is definitely going to be a challenge. As if that wasn't bad enough, I want to take a step back and take a look at some of the standards we talked about earlier. There are a couple of standardization bodies that have looked at RSE already. We've talked about 3GPP and RAN 4. And the FCC is the second body that I think is a little bit further ahead than 3GPP. We'll get to that in just a second. But as a quick review, with 3GPP, RAN 4, this is where we found the user equipment and base station requirements. And what I want to point out is if you look at the specification document and all the requirements within, it's not testing just to the fundamental frequency. 3GPP actually requires that you measure up to the second harmonic. So if FR2 frequencies are going up to 53 gigahertz, the test specification is requiring you to measure up to 106 gigahertz in that case. Now, I mentioned quickly earlier that the limit was around minus 13 dBm. You can see on the slide there that that shows up again for both 3GPP and FCC. Now, a quick note on FCC, similarly, we're not measuring just up to the fundamental frequency. They're a little bit more conservative and say that you have to measure all the way up to the 5th harmonic. So now you're getting up to very, very high frequencies. And the way that you actually read this standardization document is that if your device, your intentional radiator, is operating at frequencies less than 30 gigahertz, you only have to measure up to 100 gigahertz or the 5th harmonic, whichever is lower. And similarly, if your device or intentional radiator has frequencies above 30 gigahertz, you only have to measure up to 200 gigahertz or the 5th harmonic, whichever is lower. And again, that minus 13 dBm limit comes up. You will see those in graphics within this presentation. So at this point, we understand some of the challenges that 5G brings, and we understand that in the case of FCC, we have to measure up to the 5th harmonic, which is well over 200 gigahertz if you're measuring millimeter wave frequencies in the FR2 band. What would a solution look like in order to perform this kind of testing? This is one general layout, if you will, for a suggested solution where a bunch of different pieces of test equipment are involved. Now, this presentation is about EMI test receivers, but that's just one building block of an entire system that can address these challenges. So what you see here is a system fueled by EMC software and, of course, a receiver, which we'll be focusing on, but also a call box, an RF switch, and a signal generator to drive everything. Another thing I want to point out is that you have two sets of receive units and multiplier units. If we're talking about RSE testing that goes all the way down from the kilohertz or megahertz range up to 200 gigahertz and beyond, from a hardware perspective, it's not realistic to do that entire frequency range with one set of hardware products. It would be better if you can slice that frequency range into different sub-ranges. So you may have receive and multiplier units at 30 gigahertz, some up to 80 gigahertz, and so on. I'm using general numbers here, but this is one good approach to it. But yet the fact remains that we have to go so high up in frequency, and test receivers these days on the market only go up to 40, maybe 44 gigahertz. This is what I want to focus on for just a second on the left-hand side of the slide. We're going to address that right now and see one way that you can get past this challenge. And if you look closer at this block diagram, you'll notice that there's an LO and IF connection coming out of the EMI receiver. LO standing for local oscillator and IF standing for intermediate frequency. If we can actually do some kind of down conversion or up conversion directly from the receiver, we may be able to measure up and beyond 44 gigahertz, and this is exactly what can be done. We'll look at some details on the next slide. One way to extend the frequency coverage of your EMI test receiver is to use harmonic mixers. There's a particular option for the ESW44 called the B21 option, which you can see on the slide here, that utilizes a set of different harmonic mixers that allows you to go up to 500 gigahertz. Historically speaking, this option has been around for quite some time, actually, for other common use cases like automotive radar testing, for example. That's typically in the 77 gigahertz range, and other aerospace and defense applications for interference analysis. Sometimes that's in the 110 gigahertz range or higher. But in this case, now 5G is coming, and we know from the RSE specifications that we need to measure up to the 5th order harmonic, or 200 gigahertz, whichever is lower. So this gives you more than enough headspace to do that. And as we just learned on the last slide, you typically want to cut that frequency range into multiple different stages. So I would suggest that you need multiple different harmonic mixers to cover all the different sub-ranges. This at least gets you around that challenge of not having a receiver natively, the base unit, being limited up to 44 gigahertz. This additional option with some LO and IF connections right there on the front of the instrument, that allows you to go up to 200 gigahertz and well beyond that point, gives you a little bit of future growth. One major challenge with this approach, of course, has to do with the fact that you're up in the millimeter wave frequency band where you're going to need additional sensitivity. If you dig even further into the RSE requirements, you'll see that everything suggests you're going to need certain sensitivity at a particular test distance. This slide gives you some preliminary findings from Roden Schwartz about what it takes to measure at a test distance of 1 meter with a 1 megahertz resolution bandwidth and using an RMS detector. Now there's several different limit lines here. We've talked about 3GPP. We've also talked about FCC. This slide happens to include some RSE requirements. There's things called early pass-fail limit lines, and of course you have the real limit lines as part of the specification. Ideally, you want your sensitivity to be underneath all of those limit lines. As you go further up in frequency, it gets more and more challenging. We think that we have found an approach that will work, and it covers both FCC and RSE for minus 13 dBm per megahertz, that limit line, that same thing that we've seen in 4G and in prior years with other cellular technologies. And since there's actually a gap between the sensitivity graph and the first early pass-fail limit line, that margin allows you to use faster measurements, and you would do that with resolution bandwidths that are greater than 1 megahertz. So this is all very good news. Of course, if someone needs to perform 5G FR2 measurements up into the 200 gigahertz range and beyond, they won't be waiting around all day for that measurement to finish if you can use a reasonable resolution bandwidth. So this is just an early look at what might be possible. Let's go ahead and move over to talking more about why an EMI test receiver can be helpful for these type of tests. At this point in the presentation, we've pretty much covered everything we need to as far as 5G basics go and some of the testing challenges that have been brought our way. And we also have an idea of how to get by the frequency challenge. But there are some other things that receivers can do to be helpful. And as I just mentioned, let's go ahead and dive a little bit further into what today's test receivers can do and how that might relate to an EMI test receiver helping with 5G testing. First, let's look at the typical modern EMI test receiver design. In the past, EMI test receivers have been completely analog. And if you look at the RF section and the wideband IF section of the block diagram on this slide, all of these components are still analog. The biggest difference with modern EMI test receivers is on the right-hand side where you see the digital data section. As soon as the data passes through the analog to digital converter, now you enter the DSP area, digital signal processing. This is FPGA-based hardware where you can perform measurements and calculations much, much faster than the typical analog approach. So now with that, you can have features and functionalities, including but not limited to time domain scan, which is based on the fast Fourier transform. We're going to talk about that here shortly. You can also have real-time processing and all kinds of new displays to take advantage of the speed of that DSP hardware. Let's go ahead and look at time domain scan in a little more detail. As I just mentioned, time domain scan is based on the fast Fourier transform known as FFT for short. The FFT is actually a type of discrete Fourier transform, which is a numerical mathematic method that calculates the spectrum for a periodic signal. So in real life, we live in the time domain. With FFT, we can transfer that over to the frequency domain where calculations are a little easier to understand. What is so powerful about using the FFT is depicted by the graphic at the bottom of this slide. Like I said, we live in the time domain, so if we sample a certain number of different points, before we had FFT, we would have to fix the receiver to a certain frequency, dwell for a certain time and measure, move on to the next point sequentially until we've met all of our different sample points. With FFT, you can define this time window, which is really defined by an FFT bandwidth, for example, and several of these time points that you have to sit and dwell at and measure are going to sit within that window, and in one shot you can scan across all of those frequencies at one time, perform your discrete Fourier transform or fast Fourier transform, and then get your result out in the frequency domain. It's much, much faster, as you will see on the following slides. Let's look at those details now. On this slide, you were presented with concrete data that directly compares an EMI test receiver using a classic frequency stepped approach to this FFT-based time domain scan approach. For this particular data set, we are measuring within the commercial CISPR band, band B to be exact. You can also see in the table which weighting detector was used, how much measurement or dwell time was used, the measurement bandwidth, and so on. But a couple things I'd like to point out at the bottom of the slide, you can calculate your number of points for a classic frequency step scan by dividing your measurement bandwidth by 3. With time domain scan, the frequency bin, if you will, is the measurement bandwidth divided by 4. What that suggests, and you can see it in the table, is that with time domain scan, you end up taking more points for the same measurement area or frequency range than with a classic frequency step scan. But if you now look kind of toward the right of that table and compare the time it takes to perform those scans, time domain scan is actually faster. Now we do the math for you, and I'm looking at the most extreme case in the top row of the table. Time domain scan is literally over 9,000 times faster than a classic time or a frequency stepped approach, which is very, very impressive. So with time domain scan, you're actually measuring more points in much less time, leading to a significant time savings. In that particular example, it's 17 minutes. But if you look at the bottom of the table for a much wider frequency range, it leads to a 403-minute savings. So I think you can see just from this small example just how valuable time domain scan can be versus a classic frequency step scan approach. Just to reinforce that point, let's actually look at a real-world example where we're trying to capture a pulsed event. On this slide, you can see what measurement conditions there are. We're looking for a pulse, which is 10 microseconds long, and it has a 10 millisecond pulse repetition interval. We should be able to find it at 700 megahertz. Now, on the test receiver itself, we're going to sweep from 30 megahertz to 1 gigahertz. You can see the resolution bandwidth there used is 100 kilohertz. And as I mentioned earlier, a very typical filter used in EMC, in this case for mil standard 461, is a 6 dB filter. Now, if you go look into the mil standard spec and you do everything according to the rules, the specified sweep time says that you should use 146 seconds to complete 30 megahertz to 1 gigahertz in these particular conditions. What we will see is that there is a high probability to capture the pulse signal, and it really will take about 2 minutes and 26 seconds. I'll go ahead and start the scan here. Along the bottom part of the screen here, you can see that we are starting at 30 megahertz and stopping at 1 gigahertz. At the top of the slide, you can see the resolution bandwidth was set to 100 kilohertz, and the sweep time calculated for this particular example is 146 seconds. At this point, I can let the scan run all the way across the screen until we find our pulse at 700 megahertz. And just for full effect, I'll go ahead and let you watch this, and I'll pipe up once we see that pulse. At this point, we're approaching the 700 megahertz mark. We should start to see some of that pulse hitting the front end of our receiver. And because we're using the specified sweep time, we're guaranteed that that will hit where we are measuring. And sure enough, we do see roughly 75 dB microvolts on that pulse signal. We're going to go ahead and let the scan finish because the specification asks us to go 30 megahertz to 1 gigahertz. We have to let this scan complete to see if we find anything else. Now that the scan is complete, I think we can agree that we did find the 10 millisecond pulse signal, and it took roughly 2.5 minutes. Okay, now let's perform that exact same exercise, but this time we're going to use the FFT-based time domain scan. So as you can see on the slide, we have the same measurement conditions, 10 microsecond pulse, 10 millisecond pulse repetition interval. We should find it at 700 megahertz. We're going to sweep from 30 meg to 1 gig, same filter, same resolution bandwidth. The specified dwell time, if you look at the mil standard specification for a time domain scan, should be 15 milliseconds. I think you would agree this is significantly less than what we saw on the last slide, where it took roughly 2.5 minutes. So let's see what that looks like. I'll go ahead and hit this video. The scan will start and end already. We're finished, and you can see this screenshot looked exactly like what we saw on the last slide. I think you would agree the observations section of this slide says the event was detected and captured within seconds. The scan itself only took 15 milliseconds, but of course there's time to display and all this stuff. This time domain scan approach is much faster and less likely to miss an intermittent event, because something I haven't mentioned is with an FFT approach, you're actually overlapping multiple captures over each other to avoid something called the picket fence effect. And because you're capturing so much faster and you're getting more data than a classic frequency step scan approach, you have a much higher chance of capturing an intermittent signal within your frequency range of interest. So this is all very good news, and at the end of the day, you get your job done faster. Now I'd like to switch gears a little bit and talk about the concept of pre-selection. Any EMI test receiver in the market that claims to be fully compliant will have a preselector in its hardware path. And this is something that differentiates an EMI test receiver from a spectrum analyzer in many, many cases. My disclaimer right up front, I'm not going to say that spectrum analyzers don't have preselectors. They do, but it's for a different purpose than EMI test receivers. With EMI test receivers, everything is about avoiding mixer compression so that you minimize the chance for getting incorrect results. And what I mean by this is depicted on this slide. So if you imagine you're looking at the front end of an EMI test receiver, every possible signal is hitting the mixer in that analog section of its block diagram we looked at a few slides ago. If one of those signals, whether it's the fundamental frequency or the harmonic, maybe even one of the spurious emissions that we talked about in the RSE section of this presentation, it could lead to wrong results because you may compress that mixer. If there was a way that we could filter out all of the unwanted signal energy and just look at the particular frequency that we do want to measure, that would be ideal. And that's exactly where preselection comes in. Preselectors are designed to protect the front end mixer and help eliminate compression. Now, one thing I like to point out when I tell customers and people about this concept is you can see in the right hand graphic here that the small narrow black filter, if you will, that represents the signal we want to measure. But the much wider, taller, red looking filter, you can see isn't as narrow as what I ideally want to look at. In fact, I even let in one of the harmonic signals in that graphic, but I have slashed out 5 of the other things that were hitting my mixer before in the left-hand graphic, but now I've effectively gotten those out of the picture, filtered them out to alleviate any chance of compressing my mixer on accident. This is the entire idea behind preselection. I'd like to go in a little bit more detail on what this actually is. In short, a preselector is essentially a bank of bandpass filters that are switched into the receiver's block diagram path automatically. So as a reminder, over on the left-hand side of the slide, you can see that front end of the analog section of a test receiver. You have your front end input. That signal goes through a preamplifier and then it immediately hits this preselector, which is again a whole bunch of different bandpass filters that you can choose from. I included an example from the ESW26 here on the right-hand side of the slide, and you can see there are several actual hardware paths that the receiver can choose from. Now, With our receivers, you can choose it manually, or like I said, the receiver is capable of choosing one of these paths automatically for you. So if you wanted to measure at 250 megahertz, for example, if you go look at the table, you'll see that there's a filter for 230 megahertz to 300 megahertz, and the receiver would be smart enough to switch you into that path and reject anything outside of that bandpass area. This is extremely useful for the reasons that we looked on the last slide, but I think it's best to reinforce it with a real-life example. In this example, we'll be sweeping from 400 megahertz to 1 gigahertz with a resolution bandwidth of 120 kilohertz. Now, what you're going to notice is that the video shows that we have the preselector off, and we're in spectrum analyzer mode. That's interesting because we're talking about an EMI test receiver. If it's fully compliant, you can't turn preselection on and off in receiver mode, but you can in spectrum analyzer mode. So at this point, we're saving the trace with the preselector off. We're going to switch back and we're going to turn on the preselector by clicking this button. And then we're going to rerun that trace. And what's interesting about this is the input signal has not changed. All we've done is turn the preselector on. And as we go through the 400 megahertz to 1 gigahertz frequency range, you can see just how different these two traces are. And it was simply because in one case, our mixer was getting compressed, we were getting incorrect results, and in the other, we weren't. So you can see at certain frequencies, you would have a major difference in amplitude, which could cause you to fail a particular limit line for radius spurious emissions or any other typical EMC measurement. So in summary, for preselection, of course, we talked about this as a major difference in architecture between an EMI test receiver and spectrum analyzers. And really the whole purpose of having preselection is to reduce an opportunity for incorrect results. Okay, so at this point, we've reached the end of the presentation. To summarize, we went through three major parts of the presentation. We started with some 5G basics where we talked about FR1 and FR2. Then we explored the testing challenges where we realized FR2 goes up to 53 gigahertz. And if you really look at the standards from 3GPP, ETSI, and FCC, in some cases, the most conservative parts say you have to test up to 200 gigahertz and beyond. We learned that to get past that, you can use harmonic mixers. There's a proposed solution from Rohn Schwartz that actually gets you up to 500 gigahertz, allows you some additional headroom. And we also learned more about why you might want to use an EMI test receiver versus a spectrum analyzer. Two things that are extremely useful. Preselection prevents an opportunity for incorrect results because it's filtering out unneeded or unwanted signals that may be harmonics or spurious emissions. And time domain scan speeds up your measurement time, in some cases, depending on what frequencies you're measuring, up to 9,000 times faster than a traditional frequency stepped scan approach. So with all of that said, I hope I was able to successfully answer the question of the day: how can EMI test receivers help with 5G testing? Of course, I did mention that if your only requirement is performing RSE type tests, you can use a spectrum analyzer, but there is a convincing argument to use an EMI test receiver, and I hope that you'll consider that in the future. At this time, I'd like to say thank you for attending today. I really appreciated the opportunity to speak to all of you, and let's see if there's any questions I might be able to field with any remaining time.
You said spectrum analyzers have preselectors, but for a different purpose. What's the difference?
Good catch. I think where I'll start is you have to understand EMI test receivers typically characterize unknown signals in a repeatable manner, and typically you're testing against a standard. Whereas with spectrum analyzers, you're really mostly concerned with making accurate measurements of known signals. You typically know where they are in frequency, but the thing is with spectrum analyzers, during the frequency conversion, receivers and spectrum analyzers alike are both based on the heterodyne principle where you have a local oscillator driving a mixer. Spectrum analyzers may generate image frequencies during that frequency conversion process, and having a preselector and a spectrum analyzer is all about image rejection and making sure that that doesn't mess with your signal integrity. So whereas with EMI test receivers, where you want to have overload protection, so that you don't compress your mixer unnecessarily. With spectrum analyzers, you're really trying to lead to improved signal integrity via that image rejection, having a preselector in the path. But great question. Thanks for that.
Is the external mixer option available for all Rhodian Schwartz receivers?
No, that B21 external mixer option is only available for the ESW family of receivers at Rohde & Schwartz. In particular, the ESW has 3 different frequency base units that you can pick from, which are the ESW8, ESW26, and ESW44. This option is available for the 26 and 44 gigahertz base units, but you cannot purchase this for the ESR or the ESRP or the ESL families. The ESW is the only one that allows you to have those front panel connections for LO and IF.
When you were talking about the time domain scan, where did the specified dwell times come from?
Right. So when I was going through the example of finding a post event at 700 megahertz using time domain scan, we were actually referring to the MIL standard 461 standard. If you go dig into that specification document, you'll find something called Table 1, where you'll have a set of different requirements or specifications for a frequency scan stepped approach versus an FFT based approach, which is of course referring to time domain scan. The standard tells you exactly how to calculate the sweep time required for your frequency stepped scan approach, and then for time domain scan, you basically apply a factor based on which frequency range you're in. I actually showed those calculations on the slides early in the presentation, and you can kind of figure out where those numbers came from. I believe off of memory, for time domain scan, it was 15 milliseconds, and for frequency step scan, it was roughly 2.5 minutes, and can show you exactly how we got to those numbers.
Is the FFT approach accepted by EMC standards?
Yes, actually, time domain scan, which is of course based on the FFT, is officially recognized by MIL standard 461. I think it's a great time to mention that Rohde & Schwartz had heavy involvement in working with the Tri-Services Working Group to get time domain scan officially into the standard. And these days, we're still working with other committees and standardization bodies to get time domain scan accepted by other standards. So hopefully in 6 months to 2 years from now, we can say that even more standards officially accept it. But I think hopefully you see the time savings and all the benefits that time domain scan brings. This is good news so far.
Our thanks go to Jeremy Klein for taking time out to enlighten us about modern EMI receiver measurement concepts and 5G MmWave Spurious testing. We have a webinar coming up 1 week from today, April 23rd at 3 p.m. Eastern, covering wireless coexistence measurements and challenges. If you haven't already done so, make sure you visit our website to register for this webinar if you're interested. On behalf of Washington Labs Academy, thank you all for attending. Enjoy the rest of your day and be safe.